Today I want to talk about the Henderson-Hasselbalch equation, which is a really useful equation that we can use to find either the pH of a buffering system or, really more importantly, if I want to make a buffering system with specific characteristics, like a specific pH value, then Henderson-Hasselbalch is the way to go. So Henderson-Hasselbalch relates to a concept that I need to introduce called pKa. And if we recall that the pH, where the power or potential of hydrogen, is equal to the negative log of the concentration of hydrogen or hydronium in solution. So if I have the pKa, then the same kind of logic applies. The pKa is equal to the negative log of the Ka value. And this is interesting and useful information because we've already talked about in prior videos how the Ka value actually gives us an indication of the strength of the acid and the base. So this information, this quantity, actually gives us a little bit easier of a number to get our heads around. So if I look at the Ka value and have something on the order of magnitude of 10 to the negative 11th, that's just kind of a weird number. It's hard to get your head around. We know it's equal to the concentration of the products over the concentration of reactants, so that's pretty small, and you're kind of doing some mental gymnastics to get there. When you take the negative log of that value, it gives you a value that's in a range that's a little easier for us to get our heads around. So scientists tend to like to use pKa and then pKb also, which I'm just going to show here is the negative log of the Kb value. So if we're talking about weak base equilibria, then that's kind of where that fits in. So these two values are used by scientists in the same way that the pH scale is used by well, everyone, really, everyone kind of has a sense of the pH scale. We know that it's a 14-point scale. We know that the low numbers are acids and the high numbers are bases. And even if you don't know kind of what the calculation is, you have a sense of what the pH scale looks like because of the way that you've interacted with it. And the numbers are prettier. They're whole numbers. They're just easier to get your head around. Same is true for scientists with pKa and pKb values. They're just easier to use. They're easier to manage. And the Henderson-Hasselbalch equation, which I'm just going to show is the HH equation here, good old HH, is super useful because it says that the pH is equal to the pKa, so this is relating the two of them together. If we know the Ka of our acid system, then we can get to the specific pH, plus the log of the concentration of the base, the conjugate base, whatever the base component is to our system, over the concentration of our acid. So remember that a buffering system is made up of an acid with its conjugate base. So we're going to have specific concentrations of both of these in a buffering system. And if I take that ratio of the concentration of base over acid, take the log of that, add that to the negative log of my Ka value, then that's going to give me the pH of the overall system. So it's handy because I get it all in one fancy equation, no icebox required. In one of my former videos, we went through the icebox, and that is one way to do it. But if we have all of this information, then it's kind of a quickie little shortcut, and it also has some other value that we'll talk about in just a second. So let's solve a problem, because we're scientists. So let's look at the pH of a buffer containing, we have acetic acid here, we have a concentration 0.4 molar, and 0.2 molar sodium acetate. So you're given the Ka value. And if we use our Henderson-Hasselbalch equation, then we can say that the pH is equal to the negative log of the Ka value. So that's my pKa, which is 1.7 times 10 to the negative 5th. Again, given to you or easily look upable if we're thinking about normal, everyday, weak acids. There's tables for such things. And then we're going to add to that the log of the concentration of my base, which the conjugate base for acetic acid is the acetate ion. This is 1:1, so the concentration for the whole is going to be equal to the concentration of the acetate ion by itself. So we'll have the 0.20 molar here over the concentration of my acetic acid. Okay, so this is just a number that we can plug into our calculator. This is just a number we can plug into our calculator. When we add them together, then we end up with a pH of I have 4.5 in my notes, but it looks like it would actually be 4 point, what is that? 445, 44. Well, let's just run the numbers. So it's 4.769 is this guy, and this one is 0.301. So the reason that I'm doing this is I don't like this guy because it doesn't have enough sig figs. This only has one sig fig. And this is what happens when you trust your calculator, right? We don't test our calculators here. So if we subtract this, then we should end up with, that would be 8, 6, 4. Okay. So we'd actually end up with 4.468. This would be two significant figures. Looks like we're going to be rounding up from this guy. So that would give us a pH of 4.47. With 2 sig figs. And again, the 2 sig figs are coming from our concentration values there. All right, so this is interesting information because then I didn't have to run it through an ice box. Again, I just have a nice handy equation here that I could play around with. So I did that. And the other interesting bit is I could say, well, I know the pKa of my system because I know the Ka of my system. I know the target pH I want. Maybe I want a buffer with a target pH of 8.0. So I would plug that in, and then I know what concentration I have of my acid, so what concentration of my base would I need to make that buffer? And then you would just plug in that value. So that's kind of interesting, useful information for practical hands-on applications in the lab. So this would be one way that we could do that if we're looking for specifically targeted pHs of buffers, which again are really important for biological systems. It's really important for being able to create the conditions that we need for stasis or for equilibrium, or to avoid those wide swings in pH, which is really the goal of buffers. That's what buffers are good at, and that's what we use them for. All right, so that's Henderson-Hasselbalch, kind of a quickie way to get to the pH given our concentrations of our system. You may not be given nice, fancy, easy concentrations. You might be given things like you started with 50 mils of this particular concentration of an acid and 20 mils of this particular concentration of a base, and you'd have to find these concentrations. But again, that's still avoiding your icebox, which is kind of a nice way to go. All right, any questions on that? Feel free to drop me a line. Otherwise, I'll talk to you guys again soon.